I will start now just to make some reports about the TNEs we achieved in Grenoble-Inp. And I would like to associate to this presentation Thibault Louis, Patrick Medreau, Cédric Masclet, Philippe Marin, and others from the lab, but mainly all these guys who participated to the organizations of these TNEs. I will make quite different presentations respect to the previous one because we have a big list of TNEs which have been achieved this year, and I would like to review all these projects. So I will make a short reminder about what is our platform, a few slides just to tell you and to remind what are our facilities. Then I will pass over the last period TNE reports with several TNEs. You see almost 4 TNEs. And I will come back on the current TNE projects which are under completion. We have today Vytautas Buzinskas from Vilnius University, Technical University, who is working with us in the lab. And we have already started with Kamil Sobczak some work about virtual Roman city, and I will try to show you, because it's the last opportunity to do that, where we are going with these 2 TNEs, even if they are not fully completed, but quite completed at least. So, just starting first with a short reminder and update about what is our platform. We call it Mexico. Mexico means in French, moyens expérimentaux pour la conception, experimental resource for design activities. We have in this facility some system and selections of system like the 3D stereoscopic display wall, indeed, with an haptic arm. We have a multi-touch table, we have an HMD, we have again the stereoscopic display with the haptic arm, and we have an holographic display. We have also in our room the capacity to record all what is happening in the room in order to make a fine analysis of collaboration activities and to work about this element. And you see here various pictures of the projects we already done in the past about medicine, about assembly and disassembly, about project reviews, about medicine applications again, and one TNE project which is there. You have also a list of the type of activities we are usually doing in this kind of work and with our room. What I would like to show you, if I put the mouse at the correct location, is that we invest also in new equipments. We have already a power wall, as you can see a picture of this power wall, which is a copy indeed of the one you saw in HLRS last year at the General Assembly 2 years ago. And we invest in a mini desktop, mini cave desktop. As you can see, the planners and the overall organization is here, and it will be available in the next 2 months. It should be already installed, but there are some delay in the installation, so it will come at the beginning of 2015. So this is our tools, and we processed our TNE projects mainly with all these tools when they were necessary and available. So I come back in the last period from February to now. We had 4 projects, 4 TNE projects. The TNE 138 about advanced visualization tool for the collaborative replanning of services delivery at home with application to home healthcare. Indeed, it is a continuation of a past TNE project. We had also the TNE 22 about the assembly simulation using haptic device, which was processed by Robert Jacob from Polytechnica University. A project TNE 123 about visualization for non-convex multi-objective optimization, which was conducted by Giubittini Grozina from the University of Vilnius. And we made some work with the Transnational Access Project 107 about the last super interactive project, which was the experiment 2 in Visionair. There was already one experiment which was made in the University of Essex at the beginning of Visionair, and this is a continuation of the same project with Franz Fischnaller from the Fabricators company. So let's go inside this project here. First, with the project of Ettore Lanzarone, the context is clearly that in the region of Como in Italy, they practice home care system with a set of nurses, a team of nurses who are working and are driven to go to the patient directly at home. In this case, the schedule of work by these nurses is driven by an optimization algorithm which anticipates a week of work every weekend, so they can plan to all the work of the nurses for 1 week and for the next week. But indeed, during the week, there are some replanning which is necessary to react to some random events, which is achieved by planners in a specific office where 4 planners must collaborate. And the main research question is to be able to provide a new collaboration tool to support this collaboration activity in order to make easier the decisions that they have to face, which can become complex in some case. I will show you a little bit the idea just after. So this project is the second phase of the Transnational Access Project 29, where we already created a part of the elements, but we were not able to analyze the complexity of the situations, and it was expected to come back in order to make some experiments about the usage of what was done before. What was the case before the Transnational Access Project? The 4 planners are in an office and they can analyze the results of an optimization tool by using this kind of interfaces, user interfaces, which just list the schedules of the planners. And you can imagine that this kind of list of information, it is quite difficult to clearly identify what is the schedule of all the nurses you are in charge. And after that, if there is a problem in one list, which is managed by one planner, they have to collaborate together in order to find the best solution to re-affect the various nurses and maybe to exchange nurses from one location to another location. In this case, when you take a decision, you must deliberately violate some constraints because the system that will not find a solution with an available degree of freedom in your set of data. You need to have some violations of constraints, and the optimization in this case does not work anymore. So there is a need of oral communication. What we proposed was to remove the interfaces of the 4 planners and to push this interfaces and collaboration space into a multi-touch table, which was allowing to play with 4 persons around the table. You can see the table on the top right, and the organization of a tool which has been specifically developed for this activity, where you have mainly the map this time, which is the main metaphor which is provided to the planners, with some dots which represent the nurses and the patients, the patients of homes, and the nurses' locations, which are followed by GPS. And the followers, the planners, have on a private space around this table, on the 4 sides of the table, the capacity to see the planning of a specific nurse and are able to change this planning and to associate this planning. So we have a common map, the patient and nurse with visible status on this table, and we are offering modifications because on our multi-touch table, we know who is typing on the multi-touch table because there is a sensor on the seat, and when one people is touching the table, we can recognize that the finger is belonging to one person. So the fourth person will have know all the authorizations depending on the decisions and the area they are working on. Based on this system, which was already partially created the first time, we analyzed the system through several experiments, and we identify that the optimal graphical layout is independent from the use case and experiments. So the graphical layout with the map was something which was very important to enable collaboration and was very tangible for the planners. Also, the visualization of the nurse rules is a major item. It's not enough to put only the position of the nurse, but we can design and draw all its trajectory, the scheduled trajectory through polygon line, and this is a major metaphor in order for the planners to make decisions. Then it was also demonstrated through the experiments that just the current day information was expected. We do not need the past history and the next day information to rearrange the planning sessions, and we have something where decisions are taken in local during the day. At last, but not least, sharing information allows collaborative structuring and facilitate joint solving, which was clearly useful for the planners and validated by the planners themselves. That means that we invited the real planners in these discussions to assess the new interface, and they clearly agreed about this interface that should be deployed in this system in the next month. So the development should go ahead. And clearly, this was the main results of this project now, because we have the validations with this second TNA. So this is a short overview of the TNA 138. Then I will go quite quickly because you already have some presentations at the last General Assembly of the project, the Transnational Access Project 22 from Robert Jacob, where the main research question was to compare the process of assembly simulations or about training the assembly process. We have these two elements of context, and the question was to compare an expensive active arm, here the action arm, with a sensitive active arm, which is on the right here. So a quite cheap system respected to a much more expensive system, and to make the difference between both for this kind of applications, to see if we can overpass the use of a very expensive system. For that, we created two experiments. The first one, which is on the assembly of the screws on a very specific plate, with the idea to put the screws directly on the holes through the interactions of the haptic arm. And this system was just made for training people before an experiment, which was done to assemble the system you have on the left. So here, the work we achieved was the development of the environments to manage the collisions and the kinematic joints of the system, because we did not have the system in Grenoble before this work. So we completely developed the application to do that, and we develop a specific system where the kinematic joints are discovered in real time during the simulations of the collisions. We also defined the scenario to assemble the system, and we made the experiments with 20 participants who filled a questionnaire to get a qualitative assessment through this questionnaire. So you see here the simulation which is running simultaneously, but it is very slow with a video conference, so maybe does not work so well. So we have collisions detections. We can push the objects just by moving the other ones, and we can assemble various recognitions of the kinematic joints, and we can fix the positions of the object. Then we can repeat this kind of elements with a new part, just select the new parts and assemble it on the system. In this case, in this experiment, we did it with a simple qualitative assessment, because there was not really docking issues, because the parts must be on the kinematic solution, so we are not able to measure the quality of final positions, since when they are assembled, they are always at the proper position, since they are fixed by the kinematic joints or supported by the kinematic joints. So here it's okay. The main results that were that we have still some problems remaining with the collision detections, and our system, which detect collision, is not so good as we can expect for the moment, so we will have to work for that. But indeed the parts in here were easy to assemble, thanks to the kinematic guidance and stereoscopy display, which is helping a lot in order to position and to have relative positions in 3D. What said the users is that they have the tendency, it's easier to perform the assembly task with a basic device. This basic device has the specificity not to have haptic feedback in all the directions. We can have haptic feedback in the translation, but not for the rotations. And the overall feeling of a person was that the basic device was easier to use, maybe because it was installed with a sit-down positions and a quite comfortable position, like a mouse position indeed. A second point in here was that it was really important to have a sufficient large working space, and in this case, which was comparable to the human size, in this case, the sharp haptic arm of Apsion was a better tool than the basic device, which has a shorter definition. And if we play with scaling effects, it does not work so well. So this was the main conclusion of this second transnational access project. Let me go on the next transnational access project, which was from Grazina Giubitiene, from the University of Vilnius, who was doing something completely different from the two previous work. She is working about optimization algorithm with holistic techniques, and she was expecting to validate her algorithm by visualizing partial results of this optimization. So she is creating optimization algorithm, and she was expecting us to see if by using visualization and interaction system it was possible to have a better assessment of this algorithm. In our case, we try to compare the capacity of 3D stereoscopy to support our visualizations and the efficiency of the ultra-high definition power wall we have now, which is 3x3 HD display. So this is just a view of the achievement. What do we do was quite easy for us. Indeed, she came with big Excel sheets, which were the results of her computations and algorithms, which are working about n-dimensional optimization problem, and it was necessary to visualize some partial results like Pareto fronts and to associate various views of these Pareto fronts in order to make several perspectives on the same problem. Indeed, the problem is in dimension n, and she was able to reduce this problem in several projections in 3D. And there it was necessary, when reducing to 3D, to make connections between several representations. So what you see on the power wall on the top here is one representation of a representation on the left, and another representation of the same results, but with optimized another projections on another three-dimensional space in the design space. And when we select information on these elements, we can see the correlations with the other elements, the other dots, in the second visualization. And with that, because in these projections the system should have specific characteristics and specific shapes, she was able to decide the convergence of our algorithm. In this case, on the top case, we can see that we made the test on the power wall, and because we had a lot of points to be visualized with very dense number of points, it was better to see that on a very very high definition of system with a better visualization. While in other example, like the example which is on the bottom picture, it was really necessary to perceive 3D. And in this case, stereoscopy, 3D stereoscopy, was providing much more sense. So that's the main conclusion, indeed, of this project. If I speak about the results, when you have a lot of points with dense representations, the ultra-high definition power wall was much more better than a 3D stereoscopic system in HD only. In several cases, anyhow, 3D stereoscopy was very good support to our analysis. But indeed, the perfect case should be to have 3D stereoscopy with very ultra-high definition, which was not available at the lab for the moment. But she appreciated this work, and she was unable to modify our algorithm and to have a better convergence of their algorithm through this analysis. So that's all for Grazina Giubitioni. It was a 6-day access, 8-day access, unit of access in Grenoble, and very short results with a quite easy to do transnational access, because the only point was to put in 3D a set of dots, which was an easy task. Let's come now to a completely different project once again with Franz Visionair from the Fabricators company, who tried to work about the last super interactive project. The idea of this project is to create some creative scenario to better understand the paint of Leonardo da Vinci that you see on the picture here. He was able, because he works for museums usually, to come in the room and to have a very ultra high definition scan of this paint, and he was able to reproduce the 3D scene of a complete room where the last super interactive is positioned now. So it was a good experience for us, because we were able to visit this room in virtual reality on our systems with a very big resolutions, because we can see even some details under the paint when we go very close to the wall, what would not be possible in the real life because we cannot access to the paint directly. So that's a very nice element. And in this case, he was expecting to create a new way to navigate in this room by using the haptic arm. The last super interactive project at the beginning was an opportunity to create a better assessment of the perspective projections, which was used by Leonardo da Vinci to create the paint and to check that the perspective was quite perfect. The idea was to rebuild in 3D the content of the paint of Leonardo da Vinci and to demonstrate with classical perspectives that can be visualized in 3D that the paint was close to the perfection. So he entered in this case, and he was expected for a show in the museum to go ahead and to have more sensations with the haptic arm. So what we did with him here is more creation of a scenario for presenting the arm. Here, for playing with a scene. Here we can go with a hand, which is the avatar on the center of the system. Here it's an avatar of a hand. We can go with a haptic arm and push on the wall itself, and we destroy the wall with a certain pressure of on the wall. In this case, we needed to create and to develop the connections between Unity, which was the location where we have the scene and the haptic arm. We integrated the 3D scene in Grenoble. It was our first experience with Unity. We created a new metaphors to handle the scenes, and we tested several solutions to handle the haptic arm up to create the demonstrator, and we tested on the 3D stereoscopic wall and on the ultra high definition power wall also. So here you see the wall which is collapsing on itself. There was some sound effects in order to get this experience. And when the wall has disappeared, we can enter the scene and go on the other side of the scene in order to visualize the back of the scene and to turn around the scene, where you see the apostles which are in the other positions. So we can navigate directly in these elements with a last view, just showing the hand avatar which is handling the system with a Visionair hand of this magic scene. So that's what was being realized. It was finalized last week in Grenoble. Just after the General Assembly, we came back to finalize these elements, and it was a very nice experience for navigating in these big scenes. Here it is on the power wall. On the stereoscopic display, it was quite nice, but with much less resolutions and much less brightness, so not the same effect as this one. At last, but not least, we are still doing two TNA projects that will be finalized by the end of January. The first one is about the virtual Roman city, which is a project from Kamil Sobczak from a university in Poland, and who is working about archaeology. And the last one is about manufacturing process with some 6 VDL robots. And I will show you what we are doing this week with Vitotas Pulsingsas. So once again, and what is interesting here is that we have two completely different projects with respect to what we do previously in the previous elements, so two new use cases. With Kamil Sobczak, we work about for archaeologists who cannot scan the complex 3D scene with scanners, with laser scanners and so on, because it is too complex for them to have this equipment on the archaeological site. And in our case, the archaeological data or the archaeological physical scene may have disappeared. And in this case, we could need to have 3D reconstructions to validate some archaeological assumptions. Here, the research goal was to identify and to execute a full process to support the arguing of archaeological stuff with visualization and interaction techniques. So he was not very well aware about these techniques, and Visionair, in this case, supported the training of Kamil Sobczak through this technology. In this case, we mainly test during his first venue, because he will come back in January. We mainly test the techniques of the photogrammetry techniques in order to rebuild some existing buildings. So indeed, Kamil came with pictures of Roman city. We supported him to create the 3D models. We supported him in learning Blender in order to add some new contents to the scene what may have disappeared and to make some assumptions about the creations of buildings. And by the end, we are able to create complete 3D models with him, which come from some parts which are scanned and some parts which are fully designed in 3D with blenders or other constructive modelers. And by the end, it was expected to be able to navigate in the 3D reconstructed content to see if it is able to make, if it makes sense, and if it can validate the assumptions with proportions, with elements like that. So you see this kind of elements and this kind of projections here on stereoscopic viewers on the right. As a result, we clearly we have been able to validate the photogrammetry, so the photogrammetry techniques for this. Here you see on the power wall the results of a scan of the column, where we can see a lot of details. We can reuse this column to create a bigger temple with repetitions of the column in the scene. We plan now in January to reapply this process to rebuild a complete site which has completely disappeared and where we have only photographs which can and pictures which have been saved from the site, because the site has been digged deeper, and then the original scene that was which is of interest has fully disappeared. In this case, we hope to be able to investigate two archaeological assumptions which were made 10 years ago, but which were not validated, and we expect ourselves to be able to have more arguments for one assumption or another one. And obviously, we hope that the assumptions of his institute will be validated by our 3D reconstructions. But in this case, we will need to add to wait for the end of January to get the final results of this story. To the last project, which is undertaken right now this week with Vitotas Pecincias, who is interested about robot path generation and visualization applications for learning and training the robots to a better path. Indeed, you can see on the right what is done by classical engineering software, who is able to mill parts through robots and to simulate the trajectory of a path, where we create these trajectories. And indeed, it occurs that there are many errors, even with this professional tool, which is Mastercam in this case, which can be up to 4 millimeters error when you have a part of 2 meters, and plenty of issues which cannot be clearly understood when we visualize in Mastercam the trajectories, because we have only the trajectories which are visible. So in this case, we will try to create a visualization checklist system to avoid physical test of the milling program and to enable an a priori correction before to realize the first part and to drill or mill the first initial part. So what we did here, we already redeveloped an algorithm which is not so new in the literature, but which was, we did not have it at the lab also, which take a kind of voxel representations of the initial workpiece. And when the tool is passing, if we are able to follow the trajectory and to simulate the trajectory, which remove the voxel which are in interaction with the tool. So we rebuilt this algorithm, and we are able to show what will be the finalized part if we avoid to take in considerations the dynamic effects and all the vibrations that could appear on the part. And with the system, we can measure directly and on a visual representations where are the main errors due to the error of simulations of a robot. And we can do that by comparing the visualization on the 3D stereoscopic display and also on the power wall. With Vitotas this week, we also go ahead with this kind of technology because we realized with the robots the real milled mock-up of this part, and we are scanning this part again in order to have a 3D model issued from the real part to see if we can compare what is obtained by visualization only and what will be obtained by comparing the physical mockup with the virtual mockup which was expected. So we will have several ways to compare the results of the visualization, and what we expect is to demonstrate that by visualization we can anticipate the errors before we have an issue on the before to mill the parts, and more efficiently by milling the part in the physical world. So for the moment we have not all the results about this project, but we can realize that the simulation time is quite important. It can take almost 1 or 2 hours to simulate the full parts milling process that we just showed before, but it is cheaper to do that than to launch a real physical milling. We clearly visualize default, and the method is very promising for operational applications that could come very quickly in the industry where milling process with robots is undertaken. And as I was saying just before, we plan to measure the defaults and to compare them with the default measure by comparing the design CAN model and the real physical milled part. And this is a process which is undergoing this week and will be finalized the first week of January after the vacations. So that's all of these projects. That means, as a general conclusion about our team, is that we will have supported by the end of the project 7 projects with a high variety of applications and expertise fields. It clearly opened for us our practices, but also our eyes about use cases and capacity of visualization and interactions. We really appreciated that, and it was really amazing and really nice, with very good new friends during the last 4 years, and mainly during the last year, because we made a lot of time between the acceptance of the projects and the start of this project due to a lot of developments each time to be able to run these applications and to make something which is quite always new for us. Even if we have a project of about conversions of algorithm, which was much more easy to do because it was just visualization of a set of points. But indeed, we improve ourselves with all these developments, and we fully appreciate all our new competencies. And we are just sorry now that Visionair does not go ahead. That's all for me. So please, if you have any questions, do not hesitate. I will try to answer. Thank you very much.
So I have one question about the virtual Roman reconstruction. Did you consider the possibility to visualize differently the real parts and the modeled part? And did you propose several hypotheses of reconstruction in the model part? And if you have during the experimentation, if the archaeologist sees that his reconstruction is not correct, what is the process to modify the model?
Yes, so what we did at the beginning, because he has no material and Camille was not able to play with 3D. Indeed, he has no experience about that. We told him, oh, just try to create a content and we will see. And it took a lot of time for him. It was not able to do that. So we investigate with him and we propose him to say, oh, why not about photogrammetry? So we investigate photogrammetry techniques. We find some tools for that, we develop a process internally to be sure that we will be able to use photogrammetry properly. And we were able, with this process, to create through several images, not so much, with 5-6 images, we can recreate 3D objects and big 3D objects with the textures and so on. And we have validated this process to recreate this content. The second thing that will be done also in January, because we did not have time up to now, was to say, oh, why not to scan parts? Because we have several scanners in Grenoble. We can have laser scanner. We will have a white light scanner also, which is which will be delivered to us tomorrow afternoon. So we will have this new equipment also. We can do it with Kinects, we can do it with our current laser scanners, and we will try to investigate all this process for small parts, because usually we will be able to scan parts only with quite small equipments with this system, and we would like to be able to combine all together what is coming from photogrammetry, what is coming from traditional scanner and professional scanners, and what can come from 3D reconstruction in order to recreate a complete scene when the roof has disappeared, to be able to imagine the roof and to say, oh, because there are some equilibrium issues or because there are some proportion issues, we can say that the roof was like this, and this is the kind of work we expect to validate. So clearly we have several sources of information that we must recombine, and clearly the tolerance and the quality of these elements is not exactly the same from one technique to another one. With scanners we have very low resolutions, which is not fully expected. With photogrammetry, on the column I was showing before, if I put my slides again, on the column it was possible to read the engravements on the column with a technique. Here it is. So, sorry. So there are some marks which are on the bottom, which were engraved here, and it was possible to read it. So that means that even though if this column is in the reality more than 5 meters high, clearly it was possible to read this kind of details.